Kia ora and welcome to video 19 in the series Insightful Integration. This video here is going to be the first of two involving recursive integral formulae. So what I mean by that is, if you can see here, the integral Tn it depends on n, and n is a natural number. It should really stay that with the integral itself, but it says that up in there with the question. And the next part of it, so T2, so we go T1, T2, T3, etc. T2 depends on T1, and that's the relationship here we're trying to prove. So that's quite neat that we can use previous results to find future results of this integral. If you wanted to find T6, for example, you would have to integrate tan to the power of 12, or you'd use this recursive nature to be able to write it in terms of lower integrals of which you can find. So anyways, give that a crack and we'll see you after the intro music.
So this problem's really neat. I love the result that you can get an approximation for pi over 4, which is just the sum and differences of fractions. It's an example of a recursive integral formula. So this first thing that we're going to prove shows that the result of the integral is just related to the previous integral. And actually these recursive sequences, recursive integral formulae, sometimes the difference or the sum of two consecutive integrals exists, but the individual ones don't. In this case, we can integrate this thing. I could use Wolfram alpha and integrate tan squared or tan to the 4, and it would be tedious, but it would give me an answer. But sometimes the individual integrals themselves actually don't work, but the difference or the sum does. Anyways, that's beyond the scope of this video. Problem 19 and our problem in the next one, problem 20, is going to also be a recursive integral formula to give you some familiarity, because it has come up a few times in scholarship. Okay, so first up, rather than work out this integral, because I wouldn't even know where to start, I'm going to rearrange the expression so that it is a sum of two integrals. Okay, Tn plus Tn minus 1. I know that there is just the integral between 0 and pi over 4 of tan to the 2n of x, plus the integral between 0 and pi over 4 of tan. Be real careful here, we're subbing into n minus 1 now, but it's two lots of n minus 1 x dx. I'm going to get really bored with those brackets in a sec. And no, we know that when we integrate a sum, it's just a sum of the sum of two integrals is the integral of the sum, right? So we don't have to do two integrals here, we just do one. Okay, so we're integrating that, and there's a common factor here. We can pull that common factor out. When you factorize things that have got negative exponents, like the 2n minus 2 does, we actually pull out the lowest factor. So if I factor out the 2 tan to the 2n, I'm going to have a problem. If I factor out tan to the 2n minus 2, then this one here is going to be tan squared, and this one will just be 1. Now why is that? How has that been useful? If we go back to earlier videos in this series, we talked about making substitutions, and when you want to make a substitution to solve an integral, because I wouldn't even know about trig identities here, but a substitution, you want the derivative of the substitution to appear in the problem as well. And so if I let for my substitution here, u is equal to tan of x, then it doesn't look like the derivative sec squared x appears unless you're familiar with the fact that this dude here actually equals sec squared x. On the formula sheet, it's sec squared minus tan squared equals 1. So what we've done there is we've brought in this whole thing here is du, and we're actually just integrating a very simple expression. integral, I'll change the limits in a sec, of u to the power of 2n minus 2, because remember that u is tan of x. What am I doing? I don't need the x there. U is tan of x to the power of 2n minus 2 du, and then my limits, remember that the limits originally were x values. When x is 0, u will be equal to tan of 0, which is 0. When x is pi over 4, the u value becomes 1. Tan of pi over 4 is 1. So 0 and 1. And we're just integrating using the power rule now. Add the power, I'll add 1 to the power, so 2n minus 1 divided by the new power between 1 and 0. And, well, 1 to the power of anything is 1, so we've got 1 over 2 to the n minus, sorry, not 2 to the n, 2n minus 1. So that there is the sum of the two integrals. And remember our proof, we were trying to prove that just Tn alone was equal to the thing we've just found minus Tn minus 1. So we just need to rearrange it. If this Tn plus Tn minus 1 is equal to this, therefore Tn is this thing here minus Tn minus 1. Happy days. Square box for proof, smiley face. Okay, the second part of the problem, hence or otherwise show that pi over 4 is equal to this random series of fractions. What this requires us to do is work out a couple of these t values to start the pattern off. So go back to what our Tn formula is. Tn was the integral between 0 and pi over 4 of tan to the 2n of x. I go, well, what happens if we make n equal 0? Because it did say, I think in the problem, no it didn't, but it should have. When we're dealing with a pattern here, we're talking about natural numbers. So we've got 1, 2, 3, 4 and so on, but we could have a 0 term in the pattern. So t0 would be the first one to sort of consider. It doesn't make sense to consider t to the 1.5 or t to the negative 3, but 0, t of 0, what does that equal according to this formula? It's the integral between 0 and pi over 4 of tan x to the power of 0. So we're integrating 1. Well, that's nice. That's just x between pi over 4 and 0, so it's pi over 4. Now that's cool because that appeared in the thing we're trying to prove. And we'll just go one further than that. What's t1? T1 is the integral between, that's when n equals 1, pi over 4 of tan squared of x. It's not tan cubed over 3. The trig identity that I used before, we turn it into sec squared x minus 1 because the antiderivative of sec squared is tan. Tan x minus x between pi over 4 and 0, and that comes out to be 1 minus pi over 4. Okay, why have I just found 0 and 1? Well, we just derived a formula that says if you know one value of the sequence, you can find the next. And then if you know the next one, you can find the next, and so on. It's a recursive sequence. So what that tells us, according to this formula, which was Tn equals 1 over 2n minus 1 minus t of n minus 1, that, according to this formula, T1 is going to equal 1 minus T0. And T2, well, that would equal a third minus T1. And T3, you're going to get the pattern here, is 1/5 minus T2. And T4, one more, just so that we can really spot it, is la la la, etc. So if I look at the right hand side of the thing I'm trying to prove, which starts with a 1, take away a third, plus a fifth, and so on, right hand side of the proof is equal to 1 minus a third, plus a fifth, minus a seventh, plus a ninth, etc. So if I look at the first term in this, the 1, well, that there is just using this formula, T1 plus T0. Then I can minus off the third, which is t2 plus t1. Then I can add the fifth, which is t3 plus t2. Then I can minus the, what am I up to? Minus the seventh one, which is t4 plus t3, etc. And when I do that, the whole heap of terms cancel, right? We've got the t1 minus t1, with the minus 2t, minus t2 plus t2, t3 minus t3, and so on. And if we continue that on forever, just like the right hand side does, it's an infinite series of things. The only thing that's left is t0. And of course, t0 is equal to pi over 4. So we're done. And if you want to try it out, just go into your calculator and do this series for, I don't know, maybe just the first 5 terms. So if I go 1 minus a third plus a fifth minus a seventh plus 1/9, if I just do that, I get to 0.8349. And if I look at pi over 4, it gives me 0.785. So it's not that close for the first 5 terms, but it turns out that if you do an infinite number of terms, then it converges to pi over 4. How cool is that? Catch you in the next one.